Good morning. This is Michael Dong speaking on HPLC Autosampler of their fundamentals, operating principles, and modern trends. In this video, we welcomed LCGC International Magazine as a channel collaborator. This is our agenda. We start with an overview, which contains glossaries, requirements, characteristics, operating principle of a manual injector. Second is different autosampler types, focusing on injector designs and sampling configurations. And finally, some marketing landscape and also modern autosampler trends. I'd like to highlight the contribution of Carlston Paul from Thermo Fisher Scientific for his contribution to this video. His contribution is highly acknowledged. Here are some of the key terms and definitions. Starting with autosampler. Autosampler is a device which automates the introduction of sample solution to the HPLC column. It has two major components, which we will discuss later, which is a sample storage compartment and an injector. Injector is consisting of typically a valve, a sample metering device, and a moving sampling needle. There are several types of autosampler, such as pulled loop, push loop, and split loop design. The split loop is the most modern and is used by most modern autosampler. Most would operate in the partial loop mode rather than the full loop mode. Let's talk about sampling needle. A sampling needle can be a manual syringe, manual Hamilton syringe, typically a 22nd gauge blunt tip needle for manual injection, or most likely in autosampler is the end of a moving or movable stainless steel or peak sampling capillary in a autosampler. A sample compartment is an enclosed compartment for storing sample container, typically highly thermostated. And finally, the term carryover, which is important. Carryover is the term used to designate the amount of the main component from the prior injection sample, such as a 100% reference standard sample. And then afterward, when you inject a blank or a sample diluent or blank, typically a small peak might be observed with the retention time of the main component. That's called a carryover. Here are some general requirements and some key terms and definition. Most importantly, autosampler can automate the injection process, which is highly tedious, and it can do it very precisely. So precision is a big deal. And here we would categorize the typical sample volume range of different type of autosampler, and also their pressure rating. Typically in QC application in modern autosampler, we're looking at a precision level of 0.2% RSD to 0.5%. So for HPLC, typically for QC application, you should sample at least 2 microliter to about maybe 1 mil. For UHPLC autosample, typically you're dealing with the smaller columns, so the volume injection is much less, and you can typically inject 0.5 to about 100 microliters. And then we have a category called micro and nano LC, and we're talking about very small injection, typically not a partial loop, but in a full loop position, used mostly in research such as LC-MS application, like proteomic research. The sample flow path, typically from metals or material compatible to HPLC solvent, peaks, and other polymer. Typically, we talk about carryover characteristic of less than 0.005%. This table actually spell out some of the autosampler desirable characteristics, and some are general, some are application specific. Once again, we highlight a couple of them. So they should be easy to operate and easy to maintain. Most of them have a front panel access to sample tray and also access to key components. UHPLC compatibility is important, obviously, for UHPLC systems, meaning that the injector have to withstand at least 15,000 psi and are able to precisely inject very small volume for QC application, typically 1 microliter or less. Also should have low dispersion. Comment on biocompatibility or bioinert, where the flow path of the autosampler is made from titanium, tantalum, PEEK. The rotor seal could be made from Tefal instead of Vespel, so it's more salt and corrosion resistance. These autosampler are typically used for ion exchange application in biopharma applications such as IEC, HIC, ion chromatography, or size exclusion chromatography. Also, they are more compatible to high pH and also high salt content mobile phases. I'd like to point out that in this video, most of the material came from this white paper published in 2019, where Carlson Paul is actually the first author responsible for most of the figures and some of the contents. Also Frank Steiner from Thermo Fisher Scientific and myself. So it's HPLC, Autosampler Perspective, Principle, and Practices. It's one paper that encompasses the insider's view of autosampler. I'd like to take some time to describe the manual injector because that really makes sure that the user understand how a manual injection is being done, typically by the user kind of sampling. The user actually is the sampler, and it would use a Hamilton syringe, a blunt tip syringe, to aliquot, let's say 10 microliter from a vial by pumping it up and down, and then deliver the aliquot precisely into a manual rotor valve. Now, in the historical perspective, this Realdyne 7125 is actually pivotal. It's the first valve that actually works really well. And in several years, it basically took over the global market. So Realdyne 7125 was the standard injector in the 1980s and stretching to the 1990s. Now, what does this valve look like? Okay, this is the 7125 Realdyne valve. It is a 2-position 6-port valve with a needle port, which is central to the port, where the syringe would actually enter this needle port into a rotor, and inside a rotor seal where there's a needle seal that hucks the sampling syringe very tightly. So it's a 2-position, it's a 6-position, a 2-position 6-port valve. Here is the schematic. In the low position, you can see the 6-port, right? Typically for this valve, we connect pump to port 2, column to port 3. The sample loop is connected to 1 and 4. So you have a choice of different sample looped size from 6 microliter to 2 mil. And then 5 and 6 are actually air vent. So in this position, it's a low position where one would insert a syringe with an aliquot right in the central port, express or aspirate the aliquot right into the sample loop. It would enter the sample loop kind of backward in this position over here. And then one would manually turn the handle from low to inject, where the 6-port are reconnected. And from the pump now, you actually sweep away the entire sample loop backward, back flush it into the column. And this definitely is a historically really important sampling device. So once again, Reodyne 2125 valve is the two-position six-port valve. It has a rotor, a sample loop of your choice from 6 microliter to 2 mil, and a front-loading needle port in figure A, which is the needle port here. The rotor is turned by a handle and has connected to a rotor seal and the stator inside with 6-port also. A syringe typically is used 22 gauge blunt tip needle. Okay, you cannot use a sharp needle to introduce a sample aliquot through the needle port during the low position. A sample is delivered by switching the valve to the inject position, figure C. Okay, here I want to describe also historically kind of the first type of autosampler, which is basically mimic the manual injection process. It's kind of called the XYZ autosampler, right? Exemplified by this early design, based exactly on the 7125 valve, right positioned here inside the autosampler, right? So you have a stationary valve with the needle port, which is accessible by this traveling needle. So instead of the user actually using the needle, you have a traveling needle in the X and Y position. The X and Y position are being tracked by this screw drive mechanism, right? We allow you to access up to 100 vial in a sample tray, which is thermostated. So you have X and Y position. Z is the position of the needle, where the traveling needle can go up and down into either a flush port or a home port, and also right into a 7125 valve, right? So the needle actually should be blunt tip. So once again, looking at the figure, you have a sampling needle assembly, which connect to a sampling needle by the two drive mechanism, screw drive mechanism. You have a stationary injection valve, which can be actuated by either nitrogen pressure or by a solenoid switching valve by contact closure. You have a sample tray. This one is also compatible to a microplate position. So in this case study, we have a PerkinElmer Series 200 introduced in the 1990, which mimicked the manual injection process with a moving sampling needle, which can access 100 vial in a sample tray to deliver a sample aliquot into a fixed remotely actuated 7125 valve. And the sampling actually is done by an external sample syringe or a metering device over here. And one of the cons of this thing is you need to use a flushing solvent, okay, to connect that by the fluidic for the aliquot, right? And often you need an air segment to segment the aliquot from the flushing needle. So the XYZ design explained earlier in the previous slide actually is the type of injector called the push loop design, where you aliquot the sample from the vial, and it would travel right in this low pressure needle port, low pressure, and then the aliquot is aspirated into the sample loop, and then the valve would turn, and it would be injected under high pressure into the column, right? So this is very similar to that of the XYZ autosampler described earlier. So in the overview, I would say that the process mimic a manual injector, need a low pressure sample needle port. You definitely need a flush solvent. Is used to fill the sampling syringe and act as a carrier fluid for sample withdrawal and also delivery. Air gap are often needed to segment the sample plug from mixing with the mixing from the flush solvent. And here describing what happened at the low position and what happened at the injection step. The next one is a pull loop design. The pull loop design is a little bit simpler because it does not need a needle port, right? A simpler approach without a needle port on it. However, the sample consumption is quite a bit higher. An example of the design is used in Waters Acuity UPLC Classics, okay, which is introduced in 2004, right? So this is probably not used in many different more modern design. So in the later Acuity system, Autosampler, it does use a flow-through needle described later on. And here are some description in the schematic diagram. And one can follow the schematic diagram during the sample aspiration step and also the sample injection step using a rotor injector. Now, most of the modern design is actually called a split loop design, aka so it's also called integrated loop, or in Waters nomenclature called flow-through needle design. This is definitely one preferred for most modern sampler over here. Now, why do we call it a split loop, right? So you think about the sample loop, right? Typically, here the sample needle is part of the sample loop, right? So you can think that when the sampling needle is traveling to sample different vial, the loop is split. And when it comes, it will make a high pressure seal. So the key component is a high pressure seal that actually can seal up to a very high pressure to system pressure, right? So the seal have to work very well for at least a year and would be changed during preventive maintenance, annual preventive maintenance. Now there's actually two setups. One setup is where the syringe, the metering device, is part of the flow path, right? So this is exemplified, it's called A, which is exemplified by Agilent 1290 design. The other approach is the metering device is outside the flow path in the B configuration as exemplified by the Waters I-class UPLC. So once again, the schematic demonstrate what happened during the aspiration and during the injection step in a split looped configuration or integrated looped configuration. Here I want to summarize the comparative performance of different injector designs. Okay, and the features are precision, linearity, injection volume, flexibility, the amount of carryover, sample consumption, how much sample you need if you're sample limited, and also a short cycle time. Now, as you can see, clearly the split looped flow through needle design has the greatest performance, right? You can see everything is better. And explain why in today's world, almost all the modern sampler are using a split design or a flow through needle design. And once again, this table came from the white paper by Carlson Paul, Frank Steiner, and myself in 2019. In this next discussion, we talk about autosampling type, which is based on the sampling configuration, right? I explain what is sampling configuration, meaning that how it's a sample tray or sample vial being configured. So there's basically two different types with one class B dominating, right? So one of the early designs called needle vial to needle configuration, exemplified by the very popular Agilent 1100 for over 2 or 3 decades. It is the first split loop design autosampler, renowned for its precision, and used in the 1100, also in some of the standard autosampler for the 1200. So here we have a robotic arm, which is kind of slow, but you have a three-finger gripper, which brings the vial to underneath that sampling needle, right? And the high pressure sampling seal is positioned right underneath the needle, right? So you bring the vial to the needle. Most of the other autosampler using a needle to vial configuration, and there are several popular configurations, starting with XYZ, which we described earlier in the PerkinElmer Series 200 autosampler. And also you have different type of the positioning on the arm. You have the X and Y theta with the angular configuration shown here. Not can find an example on this one. And also you have a carousel type of configuration, which can fit either vial or microplates. This is a little bit, quite a bit more popular, where you have the something called the XZ direction with a rotary drive. So some are explained here. So B3 is exemplified by Waters Alliance, which dominated the QC labs for about 3 decades, and the Thermo Vanquish. And obviously B3 is good, except it's perhaps less efficient in space utilization. You know, the carousel requires more space. Also, most of these sample compartment are thermostated using a pellet device for cooling down if you have to go below the ambient temperature. Two-way to thermostat it, you can use Airstream, which is perhaps a little bit more popular, or you can use a contact aluminum blocks, heating blocks, for the thermostating portion. Now this is a big table. Basically, look at the HPLC autosampler from the 4 major manufacturers. Tell you a little bit about the marketing landscape, right? I would not elaborate too much, right? So we talk about pressure limits, a pretty comparable injection volume range, the minimum cycle time, accuracy, which is different from precision, right? They're all precise. And also sample capacity and precision at a very low level, right? Everybody can inject 5 microliter or 10 microliter, but it's very difficult to inject 1 microliter very accurately, right? So here are some specifications, and also carryover specification. Once again, this table came from the white paper. So in this particular slide, we talk about the autosampler modern trends. The big lesson is the split-looped injector design is dominating the modern landscape. Modern autosampler clearly now have much better reliability and really good performance. Precision, most spec are less than 0.5%. Routinely, one have no problem getting to an RSD of 0.2% RSD. Low carryover is important, particularly for LC mass spec for bioanalysis. Typically, one need to wash the external of the needle, the outside of the needle, right? Because after you inject 100 microliter, you definitely, some of the 100% reference standards are adhering to the outside of the needle. So it need to be washed either as a flush, in a flush port, or by dipping it into a wash vial. For high throughput screening application, you need very fast cycle, right? So a lot of injector can make a very fast injection cycle. Also, there's the emergence of something called the multi-sampler, designed for high throughput screening, meaning very short cycle, and also flexibility for both vial application, also microplate application. Some of the newer also would support automated sample preparation and liquid handling. But I would say that even though they are there, it's possible to do that. Very few people would use this type of sample preparation for pre-column deuterization, so on. Very, very few applications that I know of. And the big deal is also UHPLC autosampler, right, which have both low dispersion and precise injection in very small volume, down to 1 to 2, and even down to 0.5 microliter with a specification less than 0.5% RSD. On that note, I'd like to summarize and conclude the video by saying that we give an overview. We present a glossary requirement and some of the operating principle with schematic. We describe the manual manual injection process. We describe different type of injector design, the push loop, pull loop, and split loop, right? So the split loop is obviously the most important because of better performance and reliability and carryover. Talk about sampling configuration and the different type of sample compartment configuration. The trend is definitely towards split loop injector, dominating all the modern design. Great precision down to 0.2% RSD reliably in a daily fashion, and also the emergence of multi-samplers and HPLC compatible autosampler. On that note, we conclude our episode 15 on HPLC autosampler. We talked about the fundamentals of autosampling, operating principle, and trends. And we also welcomed LCGC International as a channel collaborator, starting from this video. On that note, I'd like to encourage you to subscribe for a future video. The next two, we will talk about CDS and also talk about UV detectors, and follow later on with other HPLC fundamental training episodes. So definitely see you next time. Thank you very much for your attendance.